Okay, so in this class, we're going to be talking about the law of cosines. Last week, we dealt with the law of sines. And if you remember, we used the law of sines anytime we were given two angles of a triangle and the side between them, but nothing else. And we were asked to find the missing information. Or if we were given an angle and a side and an angle between them. Or if we were given a side and an angle and a side between them. So when we had angle, side, angle, 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 side, or side, side, angle, those were the three cases where we used the law of sines. Now, today, if we're given three side lengths of a triangle with no angles, meaning we're given side, 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 or we're given two sides and the angle between them, meaning side, angle, side, those are the two cases where law of sines would not be helping us. We wouldn't have enough information to use the law of sines. And so we are going to use the law of cosines instead. And just a note of the triangle congruence postulates with side and angles, the angle, angle, angle case, we're never going to be able to use that to find missing side lengths because if you think about triangle similarity from geometry, if you have a small triangle and a much larger triangle with the same three angles, we don't have enough information to be able to figure out any of the side lengths there. Okay, so those triangles are similar, but we wouldn't be able to find any information about the sides. For the similar kind of reason, we were never able to use angle angle to prove that two triangles were congruent. We could just have that they're similar, but that didn't mean they were the same size. So side, 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 and side angle side cases, we're going to use the law of cosines. The law of cosines says that given some triangle ABC, as I have pictured, such that the opposite segment lengths are noted by the lowercase letter of the angle opposite, based on that, these three equations on the bottom of the page are true, and those are the law of cosines equations. Now, if you notice, they're all very similar in structure, so we really don't need all three. Depending on what angle you're talking about, you would just use one versus one of the other ones. But notice that on the ends, the letters match. So to start the equation or to end the equation, if you start with little a, you end with angle A. If you start with little b, you end with angle B. And if you start with little c, you end with angle C. The stuff in the middle involved the two side lengths that you didn't use to start the equation. So in the first equation, if I started with little a, the inside stuff has to be the other two side lengths, little b and little c, for both of those two terms, or three terms. Same with the middle equation, I used b to start, so in the middle we're a and c. In the third, we use little c to start, so in the middle we're using little a and little b. So let's actually go ahead and put this structure of a law of cosines equation into practice. So given this example here, I have a triangle with three side lengths labeled for us. We need to find all of the angles of this triangle. So here I'm given three sides, which means I have the side, side, side case, which means I wouldn't be able to use the law of sines, but I can use the law of cosines. So let's go ahead and start with finding angle A. And it doesn't really matter what order I do this in, but to find A, if I'm looking for angle A, I'm going to start with the equation that involves little a and ends with angle A. So I have little a squared should equal the other two side lengths squared and added minus 2 times those other two side lengths times the cosine of that angle A. You'll notice for little c, the side length, I made it like a scripted or cursive c, just so that it's different from the little c in the cosine abbreviation. So now I'm just going to plug into this equation. I know little a squared will be 14 squared, little b squared is 8 squared, and little c squared is 19 squared, minus 2 times 8 times 19 times the cosine of that angle that we don't know, so that has to stay angle A. Now here, we've done all of the hard work. We just have to use a calculator and simplify all this stuff. And actually, we don't need a calculator just yet. 14 squared is 196. 8 squared is 64. 19 squared is 361. Minus 8 times 19 is 80 plus another 72. That gives 152. And 152 times the 2 in front gives 304 times that cosine of angle A. I'm still going to simplify. So I'm going to add the 64 and the 361 together. So I have 196 equals 361 and 64 gives me an ending of 5. The 6 and the 6 is a 12. Carry the 1 plus the 3 is a 425. We still have to subtract 304 times the cosine of angle A. Now notice here, a lot of students sometimes are tempted to subtract 425 and 304. Please don't do that. That violates order of operations because the 304 is being multiplied with the cosine of A. So that would have to happen before you fuse it together with the 425. What I can do though is subtract 425 from both sides. Doing that looks like we get a negative 2, 2, 9, if I did that mental math correctly. And we still have on the other side negative 304 cosine of A. To isolate cosine of A, we'll just divide both sides by negative 304. The two negatives will cancel, so what I'd have left is 229 divided by 304 equals the cosine of angle A. And then to isolate A, we have to take the inverse cosine of both sides. So now I'm going to have that the measurement of angle A equals the inverse cosine of that fraction. And now is when I'll turn to my calculator. So 229 divided by 304. I'm going to take inverse cosine of that, is this 41.1 degree angle if I round to the nearest tenth place. So that finds us one of the three angles that we didn't yet know. And I'm rounding to the nearest tenth place because that was in the directions of the problem to the nearest tenth place. So now to find the other angles or the next angle, you could either repeat this process, but instead of using angle A, if I were finding angle B next, I would have just restructured the equation to start with so that I was using little b squared in the front and angle B on the end. And in the middle of the equation, instead of using little b and little c, I'd use little a and little c. But at this point, now that I have one of the angles, I have a case of side-side angle, and that means I can switch to the law of sines if I want. So if I'm looking for angle B, I could use the law of cosines again, or if I wanted to, I could realize that I can find the sine of angle B over little b should equal the sine of angle A over little a. And I'm using A instead of C because I didn't know angle C, but I did figure out angle A in the work in blue. So now I'm just going to replace this stuff. Sine of angle B has to stay what it is because I don't know angle B. Little b is still 8 equals the sine of angle A, which I now know that decimal approximation. And instead of using the rounded decimal though, I'm going to use the full decimal the calculator gave me because I don't want to create more error when I find angle B. So always use the full decimal. And that's divided by little a, which is still 14. So now to get sine B by itself, I'm just going to multiply both sides by that 8. So I'll have that the sine of angle B equals 8 times the sine of that decimal. I'll paste it in one moment, all divided by 14. And then to get B by itself, I would have to take the inverse sine of both sides. So the measure of angle B is now going to equal, and I guess once I had this decimal, I should have switched this to approximate, inverse sine of that ugly stuff inside. And that's when I would turn to the calculator again. So I'm taking the sine of this angle I still had up. I'm going to multiply that by 8, divide by 14, and then take the inverse sine of the result, which is giving me an approximation for the measure of angle B. And then direction said round to the nearest tenths place, so I'd have measure of angle B approximately 22.1 degrees. And then finally, you could again use either the law of cosines or you could use the law of sines to find angle C. But at this point, once you have two angles of a triangle, you can subtract those two from 180 degrees, and that finds you the third angle by the triangle sum theorem. So for our last angle, measurement of angle C is approximately 180 degrees minus both of those other two angles. And again, I'm going to use the full decimal rather than an approximated or worsely approximated angle. Minus that other angle we found. And so I'm just going to enter that now in the calculator. So subtracting this from 180 and also subtracting that 41 degree angle, gives us this 116.8 degree angle once we round to the nearest tenths place. And that now means I have all three angles. So again here we had to start with the law of cosines, and then we could have either used it again or we could switch to the law of sines to find the other angle, and then switch to the triangle sum theorem to find the third. But again, if your preference is to find all three angles using the law of cosine 3 times, that's perfectly fine, or twice is perfectly fine, that's up to you. So I want to do just one more example problem using a word problem this time. So the pitcher's mound on a baseball field is approximately 43.53 feet from home plate, and the distance between the four bases is 90 feet. We're looking for the distance from the pitcher's mound to first base. And there's some notes on here in case people didn't realize, but the angles formed by all the baselines are 90 degrees. The points at home base, the pitcher's mound, and second base are all collinear, means they form a straight line. And the one that's not so obvious to everyone, perhaps, is that the pitcher's mound is not halfway between home and second bases. So it's actually closer to home plate than it is to second base. So I'm going to start in this problem by labeling some things. I'm going to call home base H, angle H. First base is F for first, second is S for second, and third is a T for third. I'm going to put the pitcher's mound in line with S and H, but I'm going to put the pitcher's mound closer to H since it's not halfway between, and I'm going to call that point P for the pitcher. We're told all the baselines are 90 feet in distance, so I'm going to label that in my picture. And we're told the distance from the pitcher's mound to home plate is 43.53 feet, so I'm going to go ahead and label that. And we also knew that the angles formed by the baselines are right angles, So I can put in these right angle boxes at all of those angles for 90 degrees. What we're looking for is the distance from the pitcher's mound to first base. So that segment there is opposite angle H, so I'm going to refer to that as little h. So now we have everything we need to solve this problem. If it's going to help later on, I'm going to label the other segment lengths. So the segment HF is opposite angle P, so I'm going to call that little p. And the segment opposite angle F is our segment PH, so I'm going to call that little f. So now if I'm looking for little h, what I'm going to do is use little h squared should equal little f squared plus little p squared minus 2 times little f times little p times the cosine of the angle opposite little h, which is angle h. Now, angle h to start with was 90 degrees, but h for purposes of the inner triangle here, PHF, is angle PHF. So I could have put that in parentheses. I'm just going to put it on top so we remember that capital H is not what it was to start with on the baseball diamond of 90 degrees. It's actually this inner angle PHF or FHP. Now I'm going to realize here that when I plug in, I don't know little h and I also don't know big H right now. But because we knew that the 90-degree angle is cut by segment PH, which if we continue it to second plate is actually just the diagonal of the square we have here, then we know that the diagonal of a square bisects the angle of the square. So that 90-degree angle actually creates two 45-degree angles, which means we now know in this equation here that this big H is really 45 degrees. And rather than crossing that out, let me just on the next line establish what we now know. So little h is what we're looking for, so that has to say little h. Little f is 43.53, which gets squared. Little p is 90, which gets squared. Subtract 2 times 43.53 times 90 times the cosine of h, which now we establish is 45 degrees. So now all I'm doing is simplifying this with my calculator. So putting that stuff in, 43.53 when I square it gives this 1800 number. Put that in. I know that 90 squared is just 8100 since 9 times 9 is 81. And the rest of the stuff that I'm subtracting, I'll go ahead and use the calculator for that. So I have the cosine of 45 degrees, should be root 2 over 2, here's the decimal approximation, times the 90 in front of it, times the 43.53 in front of that, times the 2 in front of that. So this is the number I'm subtracting from the two numbers I had already recorded. So subtracting that means I'm going to make that negative on my calculator. I'm going to add the 8100, and I'm going to add the 1894.8609. And so now my result is little h squared, but I just want little h. So I'm still going to have to square root both sides in order to get my approximation for little h. So now square rooting gives this 66.74 decimal. representing little h, which was the distance from the pitcher's mound to first base. Now all that's left for me to do is following the directions, which say to round to the nearest hundredths place. So that looks like little h is approximately 66.74 feet from pitcher's mound to first base. That solves the problem.